Hello, boys and girls. So your exam date has been announced now. It is on the 26th of July. Hopefully. COVID cases in our country are increasing, but I think we have the facilities. Chalo, हमारी date तो अभी 26th of July है. So boys and girls, it's a golden opportunity for us. Tests, okay, we will have them. Just before that, just see that what you do not know and try to revise that topic. The first thing that I'm going to revise today is thermal radiations. It came at a demand from a couple of students, and let me see if I can finish it in a small lecture today, or we will have two lectures. You have all your notes with you. Those of you who do not have, please exchange it amongst yourselves. So I am also going to do something, but there will be so much which I will just speak. I've just written a few things down of what all I have to do over here. I have it with me here. Right? So I will, let's see that if we have thermal radiation incident on a material, let's say we have a material, and we have thermal radiation incident Q. Q is the total thermal radiation incident. Those of you who know it can move the lecture forward. Total thermal radiation incident. Out of which, Q1 gets reflected, Q2 gets absorbed, and Q3 gets transmitted. Right? Q1 gets reflected, Q2 gets absorbed, and Q3 gets transmitted. We define a few terms called reflectance. R as total amount of thermal radiation reflected to the total incident. We define absorptance as A, total amount of radiation absorbed to the total incidence, and we define transmittance T as the total amount of energy transmitted to the total incident, and we will have R plus A plus T equal to 1. Check Q1 plus Q2 plus Q3 upon Q, and it is Q1 plus Q2 plus Q3 which is equal to Q. And then let's assume let T is equal to 0. Therefore, R plus K is equal to 1. Which means that good reflectors are bad absorbers. Either thermal radiation will be reflected or it will be absorbed, or vice versa. Good reflectors are bad absorbers. Good reflectors are bad absorbers. Okay? Now, boys and girls, there is something called emittance. Heat is emitted by all materials. Everybody above 0 Kelvin emits heat. These are few points on Prevost theory. Emit तो ही करेगा if its own temperature is more than the surroundings. Then it will emit. Reflection, absorbance and transmittance occurs when thermal radiation is incident on a material. Then if this is kept in an enclosure of a lower temperature, then it will emit heat. It will emit only those wavelengths which it would have absorbed. Thus, good absorbers are good emitters. Anything will emit those wavelengths, it will also depend on its temperature, which it has absorbed when thermal radiation was incident on it. Right? We have now to discuss something called, let's discuss something called a black body. A black body is something which absorbs radiations of all wavelengths. A black body does not transmit any radiation. A black body does not reflect any radiation. It absorbs all the radiations. Thus, if a black body absorbs all radiations, it will also emit all radiations. It means a black body is something that when it is heated, it will emit radiations of all wavelengths. Now, how can we come close to a black body? We have something called a Ferri's black body. You know, a black body is not necessarily black in color. A black body is not necessarily black in color. But if something is black in color, it really comes very close to a black body. In a Ferri's black body, it's very interesting. We have a it's like this in the film form, cone here, and this is double walled. And this is made of length black, a material called length black, and its inside is silvered. Its inside is silvered, and we have a cone here, so that whatever little radiation will enter through this opening, will be, reflected multiple number of times. And at each reflection, a part of the energy is absorbed. Why have we kept a conical thing here? So that something which comes directly, the chance of it being reflected back through the hole is minimized. Thus, such a body, and remember that it is only the opening which is the black body. It is called a Ferri's black body, and it contains a double-walled metallic sphere having a narrow opening and a conical projection. The inside is coated with lamp black. And after so many reflections, 97% of thermal radiations are going to be absorbed. And when this body is going to be placed in a bath, a thermal bath, it will emit radiations of all wavelengths. In simple words, when it is heated, it will emit radiations of all wavelengths. We show that it is the opening which is the black body and not the entire structure. So in simple words, a black body is one which absorbs the radiations of all wavelengths, and when it will be heated, it will emit radiations of all wavelengths. We have something called the Prevost Theory of heat. I'm not going to write points, I'm just going to speak out a few points which are written here, and you can write them down if you wish to. The Prevost Theory came about in 1792. He says that everybody above 0 Kelvin emits radiations of all wavelengths. Everybody above 0 Kelvin emits radiations of all wavelengths. And the amount of energy corresponding with each wavelength increases with increase in temperature. The amount of energy emitted simply increases with increase in temperature. The total amount of energy will depend upon the sum of the energies corresponding to each wavelength. Right? And the total amount of energy emitted will increase with increase in temperature. He also says that there is a continuous exchange of radiations. Okay. He says that there is a continuous exchange of thermal radiation between a body and its surroundings. And this rise or fall of the temperature of a body is due to this exchange. And when the temperature will become the same, then there will be no exchange of heat. This is the Prevost theory of heat. There is something called Kirchhoff law. As we have just done, that if thermal radiation is incident on a material, then it can be reflected, absorbed or transmitted. transmitted, then it can be reflected or absorbed. For a black body, it will not be reflected at all and the entire energy will be absorbed. And when this body will be heated, it will emit radiations of all wavelengths. This means that good absorbers are good emitters, but poor reflectors. Or you can say good absorbers are poor reflectors, but good emitters. This statement has been collectively called Kirchhoff law. In simple words, it says that good absorbers are good emitters. This is the basic essence of a Kirchhoff law. He says, the statement says, at any temperature, the rate of emittance, at any temperature, the rate of emittance, by rate of emittance means the amount of energy being emitted per unit time, per unit area. At any temperature, the rate of emittance to the absorptance of a body is a constant and is equal to the emittance of a black body. It is equal to the emittance of a perfect black body at that temperature. Okay, I can done. At a given temperature, the ratio of the emittance to the absorptance at any temperature, the ratio of the emittance to the absorptance of a body, कुछ भी कोई भी body हो सकती है, of a body is a constant. Constant तो होगा ही, good absorbers are good emitters is a constant and is equal to the emittance of a perfect black body at that temperature. This is the statement of Kirchhoff law, that at a given temperature, the ratio of the emittance to the absorptance of a body is a constant and is equal to the emittance of a perfect black body at that temperature. Okay, let's try to prove it. It's very simple. Let E be the amount of energy emitted. Per unit time, per unit area, at a certain temperature. Q is the energy incident per unit time, per unit area, right? Therefore, amount of energy absorbed per unit time, per unit area is A into Q, where A is the absorptance. Where A is the absorptance. The amount of energy absorbed, absorptance is total energy absorbed over total energy incident. Therefore, an amount of energy absorbed will be absorptance into total energy incident. As we said that Q is the amount of energy incident per unit area per unit time. Therefore, the amount of energy absorbed per unit energy is A into Q. Right? Equilibrium is attained when the amount of energy emitted per unit time per unit area is equal to the amount of energy being absorbed per unit time per unit area. area. After that the temperature will not increase any further. फ्यूज वायर में भी तो ऐसा ही होता है, जितनी देर तक किसी बॉडी का टेम्परेचर सराउंडिंग से ज्यादा है, इट विल emit heat. But as it is emitting heat, its temperature will also fall, and the rate at which it loses heat will decrease. A stage will come when the amount of heat being emitted, or let's take the example of a wire getting heated up. As the wire is getting heated up, any material, it is absorbing radiation, let's say. At that time its temperature is less. The amount of energy being emitted per unit time per unit area is going to be lesser than the amount of energy being absorbed per unit time per unit area. But as time passes, it will absorb. It is absorbing the same amount, but it is emitting more because its temperature will go on increasing. A stage will come when the amount of energy being emitted per unit time per unit area, a temperature will be achieved when the amount of energy being emitted per unit time per unit area will become equal to the amount of energy being absorbed per unit time per unit area. Or E over, okay. E is equal to H. Now for a perfect black body or a black body, A is equal to 1. Therefore, E is equal to EB into Q. Right? Or from 1, E is equal to A is equal to 1. For A is equal to 1. For a perfect black body, A is 1. Right? Thus, E is here. For a perfect black body, A is 1. Therefore, EB equal to Q. If the black body energy multiplied by a black body is equal to Q. Therefore, this is A into EB. समझ आई बात? For a perfect black body, A is 1. EB, A is 1 equal to Q. From 1, I simply put it back again, is equal to A into EB, or E over EB, or E over A is equal to EB. This is the statement of Kirchhoff law, that at a given temperature, the ratio of the emittance to the absorbance of any body is a constant and is equal to the emittance of a perfect black body at that temperature. Simply trying to say that good emitters are good absorbers, right? Then we come on to the Newton's law of cooling, which is something very, very important, please. The Newton's law of cooling is something very, very important. अभी तक तो बातें सी, ये प्रूफ भी करने की कोई जरूरत नहीं है आपको, but it is just to give you a proof that how we apply things. Kirchhoff law says good absorbers are good emitters. At any temperature, the ratio of the emittance to the absorbance of a body is a constant and is equal to the emittance of a perfect black body at that temperature. Let's define another term called emissivity. E, the ratio of the emittance of any body to the emittance of a perfect black body. Therefore, for a perfect black body, E is equal to 1. Emissivity of any body is just like relative density. The emissivity of a body is the ratio of the emittance of the body to the emittance of a perfect black body at that temperature. For a perfect black body, the emissivity will be 1. दो लेक्चर बनेंगे बेटे छोटे छोटे, आपको भी आराम मिलेगा. न्यूटन्स लॉ ऑफ कूलिंग. Says that the rate at which a body loses heat, the rate at which a body loses if I have a cup of tea or coffee over here, the temperature of the cup of coffee could be around 7 to 80 degrees centigrade, and the temperature of the surrounding could be around 25 degrees centigrade or maybe 30 degrees centigrade. Then heat will flow from the coffee to the surroundings. The rate at which it falls, the rate at which a body loses heat is directly proportional to the temperature of the body. It is directly proportional to the difference, to the temperature difference between the body and its surrounding. The rate at which a body loses heat is directly proportional to the temperature difference between the body and its surroundings. Now, I'll just give you another example. The example is that if at all I have, a cup of coffee at 80 degrees centigrade, right? And the temperature of the surrounding is 30 degrees centigrade. I allow the cup of coffee to cool. Cool ho gayi, mere kya majal hai? Because the temperature of the coffee is higher than that of the surroundings. You have to tell me in which case more heat is lost. When the temperature falls from 70 to 65 or it falls from 65 to 60. In which case is more heat lost? जनाब दोनों में बराबर है. Newton's law of cooling has nothing to do with it. आगे आएगी बात. It is mass into specific heat into change in temperature. The cup of coffee is the same. Specific heat is the same. Change in temperature 7 to 65, 5 degrees C. 65 to 60, again 5 degrees C. Thus, it is the same. Newton's law of cooling has nothing to do with it. Newton's law of cooling has to do with the time taken for this cooling to take place. From 7 to 65 times ज़्यादा लगेगा कि 65 to 60 times ज़्यादा लगेगा. Newton's law of cooling says that the rate at which a body loses heat is directly proportional to the temperature difference between the body and the surrounding. Initially the temperature difference was 70 minus 30. Now it is 65 minus 30. It means it will take longer for the temperature to fall from 65 to 60. And the last will be from 35 to 30. Ultimately temperature 30 हो जाएगा ना, जितना surrounding का था, and then it will not emit any heat. वो बराबर हो जाएगा. पर 5 डिग्री के क्यों? 70 to 69 आएगा, तो टाइम ज़्यादा लगेगा. 69 to 68 आएगा, टाइम थोड़ा सा और ज़्यादा लगेगा. The rate at which a body loses heat is directly proportional to the temperature difference. As the temperature of the body falls, जितना टेम्परेचर बॉडी का कम हो जाता है उतना ही टेम्परेचर फॉल होने को टाइम ज्यादा लगेगा. या कह लो कि उतने ही टाइम में टेम्परेचर फॉल कम होगा. उतना ही टेम्परेचर फॉल होने को टाइम ज्यादा लगेगा, या कह लो उतने टाइम में टेम्परेचर फॉल तो होगा पर थोड़ा कम होगा. बिकॉज द रेट एट विच अ बॉडी लूजेस हीट is directly proportional to the temperature difference between the body and the surrounding. Lecture चल रहा होना चाहिए, lecture बंद. I have very less battery left, but चलो करा देता हूँ आपको मैं. The rate at which a body loses heat, an amount of heat dq is lost in a small time dt, is directly proportional to the temperature difference between the body and the surrounding. T is the temperature of the body, T naught is the temperature of the surrounding. Or you can say minus dq by dt is equal to, चलो proportionality बात ही, K into T minus T naught. This is mass into specific heat into change in temperature. dQ is mc dt. d bada T. This is temperature. It means the small temperature fall dt in a time dt. For a small fall in temperature dt, the rate of loss of heat can be assumed to be constant. Integral करेंगे ना 1 over T minus T naught into dt is equal to minus K by mc into dt. Right? Integral of 1 by T minus T naught into dt is equal to minus K upon mc is simply बड़ा. It's a constant term. थर्मल कंटिन्यूटी वाला नहीं है, सीधे कांस्टेंट into dt integral. When we will solve the integral indefinitely, it will be log of t minus t naught is equal to minus kt plus c. Whenever we solve an indefinite integral, there is one with a constant coming up, please. It means a graph between. बहुत आता है पेपर में. Simple सवाल आ रहा है. This is a straight line. Right? Y is equal to mx plus c. Along y-axis we have log of t minus t naught. This is the slope. T is along x-axis plus c. To solve questions here, we will have to use another result. Let me use integral of 1 over t minus t naught into dt is equal to minus kt plus is equal to minus k into dt. Okay, minus k into dt. We see that the temperature falls from T1 to T2 in a time t. Right? This is log of T1 minus T naught from T1 to T2 equal to minus kt. This is log of T2 minus T naught minus log of T1 minus T naught. I hope you understand this is minus kt. Let me absorb the negative sign. It will be log of T1 minus T naught minus log of T2 minus T naught equal to kt, and this will give us log of T1 minus T naught. Log m minus log n is log m by n over T2 minus T naught equal to kt. This is one way in which you can solve numericals. The data given to you is such के वो कट-कटा जाएगा, आपको log की ज़रूरत नहीं पड़ेगी. But there is another way also in which we can work things out. We have an alternate arrangement. इसे रख कर दूँ. Alternately, we will start from here. Minus dt upon dt will start from here. Is equal to bada K into T minus T naught. Let the temperature fall from T1 to T2. Final temperature minus initial temperature. Initial temperature is higher and it takes a time t. Listen to me carefully. Usually बच्चे numerical किसी तरह से करते हैं. As the temperature keeps on falling, the rate of heat loss goes on decreasing. We will assume the rate of heat loss to be a constant at a temperature which is the mean of the initial and final temperatures. Let's say the initial temperature was 50 degrees C and the room temperature was 20 degrees C. Right? The temperature falls from 50 degree to 30 degree. The rate of fall of heat or temperature was dependent on 50 minus 20. Finally, it was 30 minus 20. We will assume the rate of heat loss to be constant at a temperature of 40 degree. We will assume कि जैसे ऐसे हो रहा है कि rate of heat loss हमेशा 40 डिग्री पे था. लीनियर स्केल है ना, कर सकते हैं. लॉग वर्ड हो जाएगा. This is the variable temperature. We will assume this to be a temperature which is the mean of the two temperatures minus T naught. and this is higher temperature minus lower temperature, fall हो रहा है, taking a time t, giving me k. In this method, we have assumed the rate of heat loss to be constant at a temperature which is the mean of the two temperatures. I would have loved to discuss a numerical problem here. I don't know if I can. Okay. He says in a question that you have a cup of tea which takes 7 minutes to cool from 60 to 40. I will use both methods here. Takes 7 minutes to cool from 60 to 40. Takes 7 minutes to cool from 60 degree to 40 degree. He says find the temperature after next 7 minutes, and the surrounding temperature is 10 degrees. Remember that the Newton's law of cooling is valid only for a temperature difference of 30 degrees. But we keep using it as an approximate result. ठीक है? ड्यूलोंग एंड पिटेट ने किया था, उन्होंने कहा था 5/4 का होता है, छोड़ो नहीं पूछते आपको. So in the statement it is always written that the rate at which a body loses heat, बताना चाहिए था मुझे पहले, is directly proportional to the temperature difference between the body and the surrounding, provided this temperature difference is not very large. It is valid up to 30 degrees. A temperature difference of 30 degrees C. But we keep using it. Like in this question, it's more than 30. 60 to 40 are. Let me use both the techniques. To arrive at the answer. वैसे what do you think? 7 minutes में 20 डिग्री गिर गया. 7 मिनट में 20 डिग्री गिर गया. अगले 7 मिनट में 20 गिरेगा कि कम गिरेगा उससे कम गिरेगा. इसका मतलब the answer is less than 20 or more than 20? It will be more than 20. Because 60 to 40 आ गया, 20 डिग्री गिर गया. अगर यूनिफॉर्म रहता रेट ऑफ हीट लॉस तो 40 से 20 आ जाता, पर क्योंकि टेम्परेचर कम हो ही जा रहा है, रेट ऑफ हीट लॉस कम हो ही जा रहा है, तो वो इट विल बी एनीथिंग बिटवीन 20 and 30. लेट्स सी. पहली बार log of T1 minus T0 60 minus 10 upon T2 minus T0 40 minus 10 is equal to K into 7. ये आ गया हमारे पास. 60 minus 10 is 50 over 30 equal to 7K. दूसरी बार again. Now the initial temperature is 40 and the final temperature is T1 40 minus 10 upon T minus 10 equal to K into 7. दो बारी लगा दिया मैंने, यही चीज दो बारी लगा दी. Therefore 5/3 equal to 30 upon T minus 10. This will give you 90 is equal to 5T minus 50. 5T will be 140 and T is going to be 28 degrees C. आ गया ना? But students will say, sir, यहाँ पे अगर 7 ना होता, in the next 40 minutes होता, गड़बड़ हो जाती. Sure, हो तो जाता, पर आसान नहीं है करना. Calculation to be. यहाँ से करते हैं. Here we are assuming the rate of heat loss to be constant. करना दो बार ही पड़ेगा. First it is 60 minus 40 upon 7 is equal to K. I have assumed the rate of heat loss to be constant at the temperature of mean of these temperatures. 60 plus 40, 100 upon 2, 50. Right? Minus 10 surrounding. This is 20/7 equal to 50 minus 10 is 40k, ये 2 आ गया, यहाँ से ना k की वैल्यू निकाल लो 1/28। दूसरी बारी फिर लगाओ, T1 is now 40 minus T, साथ ही अब यहाँ टाइम जितना मर्जी हो, you will substitute equal to 1/28 into initial cost 40 plus T upon 2 minus 10. सॉल्व करके देख लेना, दिस विल गिव यू T equal to 28 degrees. मैं भी तकरीबन यही यूज करता हूँ, पर लॉग वाला भी पता होना चाहिए क्योंकि वहां से ग्राफ आता है. नो जी, दैट इज ऑल फॉर टुडे. वी आर लेफ्ट विद Stephen's law, Wien's displacement law, and black body radiation spectrum. That will be another half an hour lecture, please. Hope you like it.